a soft t-shirt, a comfortable pair of socks, a lightweight athletic shirt that feels almost ordinary against the skin. But some modern textiles are being designed to do more than simply cover the body. Certain fabrics can be engineered with antimicrobial properties, helping reduce the growth of unwanted microorganisms on the textile surface. What makes this especially fascinating is that one ingredient can begin far away from a clothing store inside mountains of discarded crab and shrimp shells. These shells contain chitin, a natural material that can be processed into chitosan, a versatile substance used in textile research and manufacturing for its film-forming and antimicrobial properties. So how can seafood processing waste become part of a soft, wearable fabric? Behind that familiar shirt is a surprisingly complex industrial journey, one that begins with shells most people would simply throw away. Antibacterial and antimicrobial textiles are designed for situations where freshness, hygiene, and odor control are important. They can be used in sportswear, socks, underwear, medical textiles, uniforms, and other everyday clothing. Depending on the manufacturing method, the antimicrobial component may be incorporated into the fiber itself or applied as a textile finish. The interesting part is where chitosan enters the story. Crab and shrimp shells are rich in chitin, a natural polymer also found in the structures of insects and other organisms. Through controlled chemical and industrial processing, chitin can be converted into chitosan. That transformation creates a material with properties that can be useful in textile finishing. Instead of viewing seafood shells only as waste, manufacturers can recover valuable components and send them into another production cycle. And now, the journey moves from the seafood supply chain to the factory floor. The first visible factory operation begins with incoming shell material, large quantities of crab shells, shrimp shells, and related seafood processing residues arrive from processing facilities where the edible meat has already been removed. The material may arrive in sealed containers, bins, or bulk transport vehicles. At receiving areas, workers and automated handling equipment move the shells toward designated processing zones. The scale can be enormous. What looks like a pile of discarded shells can represent a significant source of recoverable biological material. Before anything can become a textile ingredient, however, the shells must be separated from unwanted material and prepared under controlled conditions. The shells first enter cleaning and preparation systems. Industrial washers remove remaining food particles, salt, oils, dirt, and other contaminants. Rotating screens, water sprays, conveyors, and separation equipment help sort the incoming material. After washing, excess water has to be removed. Depending on the facility, mechanical dewatering and controlled drying systems reduce moisture before further processing. This matters because inconsistent moisture or contamination can interfere with the chemical reactions that follow. The cleaned shells are then reduced into a more manageable raw material, ready for the next transformation. At this point, they still look nothing like clothing material. The prepared shells are fed into industrial grinding equipment. Heavy-duty mills break the shells into smaller particles, increasing the available surface area for processing. The material may then be carefully measured and transferred into controlled batches. In a chitin processing operation, different chemical treatments are used to remove minerals and other components from the shell structure. The exact formulation depends on the intended material and production technology. As the process continues, the hard shell particles gradually lose their original structure. What began as rigid seafood waste is becoming a purified biological polymer that can be processed much further. This is where the major transformation takes place. The shell-derived material undergoes controlled chemical processing to separate chitin from minerals and proteins. One important step is demineralization, which removes much of the calcium carbonate naturally present in shells. Another stage removes remaining proteins and impurities. The resulting chitin can then be converted into chitosan through a process known as deacetylation. In simple terms, this changes the chemical structure of the polymer and gives the resulting chitosan properties that make it useful for a range of applications. The processed material is washed, purified, and adjusted until it meets required specifications. For textile production, the chitosan may then be prepared as a solution, coating, blend, or other textile-compatible formulation. This is the critical moment. The discarded shell has now become a functional material that can participate in fabric production. The next stage connects the processed chitosan material with textile manufacturing. Depending on the technology, chitosan may be incorporated into fibers or applied to already produced fabric as a controlled finishing treatment. In a fiber-based process, polymer solutions can be prepared and pushed through extremely small openings to form continuous filaments. In a finishing process, the fabric passes through coating or treatment equipment that distributes the chitosan-based formulation across its surface. Precision is essential. Too little treatment may provide insufficient performance, while too much can affect softness, appearance, breathability, or durability. Once treated, the textile moves through drying and curing equipment designed to stabilize the material. The result is no longer a raw polymer. It is becoming a usable textile. Before the fabric can become clothing, it must pass through extensive quality checks. Samples are examined for thickness, weight, strength, softness, color consistency, moisture content, and treatment uniformity. Laboratory teams may also test antimicrobial performance using standardized methods appropriate to the intended product. Automated inspection cameras can search for visible defects, uneven surfaces, stains, broken threads, or irregular treatment. If a batch fails specifications, it may be held for investigation, reprocessed when possible, or rejected. This stage protects more than the factory's production numbers. It protects consistency because a customer buying one garment expects it to perform like the next garment produced from the same specification. Once the textile passes inspection, it moves into garment production and finishing. Large fabric rolls are measured and prepared for cutting. Computer-controlled cutting machines can arrange garment patterns efficiently across the fabric, reducing unnecessary material loss. Workers in sewing machines then assemble panels into shirts, socks, sportswear, or other finished garments. Labels, seams, cuffs, collars, and other components are added according to the design. After final finishing, garments are folded, tagged, and packed. Automated conveyors can move products between stations while workers check appearance and presentation. Cartons are sealed, labeled, and grouped onto pallets, creating stable loads ready for warehouse movement. The packaged clothing now enters the finished goods warehouse. Forklifts, pallet trucks, barcode scanners, and inventory systems keep track of every shipment. Some modern facilities use automated storage systems that identify pallet locations and retrieve products when orders are received. The warehouse is not simply a place to store boxes. It acts as the connection between production and distribution. Different sizes, colors, styles, and product batches must remain organized so the correct garments can be dispatched at the right time. Once an order is confirmed, the required cartons are picked and moved toward the shipping area. At the loading dock, pallets are staged according to destination. Forklifts move finished cartons into trucks, containers, or other transport systems. From there, the garments enter a much larger supply network. Some shipments travel to regional distribution centers. Others go directly to retailers, warehouses, or fulfillment facilities. Transport schedules, inventory records, scanning systems, and order information keep the movement coordinated. The shells that once existed beside seafood processing lines have now become part of a completely different supply chain, one leading toward clothing racks and customers. Eventually, the finished garments reach stores, online fulfillment centers, sports retailers, or specialty clothing outlets. Inside a store, they may be folded onto shelves, hung on racks, or displayed as part of an activewear collection. A customer sees a soft shirt or another textile product. They may notice the color, fit, texture, or advertised performance, but they probably never imagine where part of the material's story began. Behind that final garment was a long chain of operations, seafood shells collected as industrial byproducts, cleaned and processed. transformed into chitosan, incorporated into textile production, tested for quality, converted into garments, packaged, stored, shipped, and finally placed into the customer's hands. And that is what makes this manufacturing journey so remarkable. Something once considered waste can be redirected into a higher value material, connecting seafood processing, chemistry, textile engineering, and everyday fashion. From discarded shells to functional fabric, the transformation is a reminder that modern manufacturing is not always about creating something from nothing. Sometimes it is about looking at what has already been left behind and finding a completely new purpose for it.